Machine learning represents a fundamental shift in how we build intelligent systems. In traditional programming, developers write explicit rules for every possible scenario. If this happens, do that. If that condition is met, execute this code. But as problems become more complex, these rule-based systems become impossible to maintain. Imagine writing rules to recognize a cat in an image or to understand human speech. The number of rules would be astronomical and constantly changing. Machine learning takes a completely different approach. Instead of programming rules, we feed data to an algorithm and let it discover patterns on its own. We show it thousands of examples, and it learns what makes a cat, or what spam emails look like. This data-driven approach is what makes machine learning so powerful, scalable, and adaptable to complex real-world problems that would be impossible to solve with traditional programming.
When we talk about machine learning, we're really talking about three distinct paradigms, each designed to solve different kinds of problems. First, there's supervised learning, where we train models using labeled data. Think of it like learning with a teacher who provides the correct answers. We show the algorithm examples with known outcomes, and it learns to predict those outcomes for new data. Second is unsupervised learning, which works with data that has no labels at all. Here, the algorithm acts like a detective, searching for hidden patterns, groupings, or structures in the data without being told what to look for. It's perfect for exploratory analysis when you don't know what you're looking for yet. Finally, reinforcement learning takes inspiration from behavioral psychology. An agent learns by interacting with an environment, trying different actions, and learning from the rewards or penalties it receives. It's trial-and-error learning at its finest. Understanding these three paradigms is absolutely essential because choosing the right approach depends entirely on your problem type and the data you have available. Supervised learning is the most intuitive form of machine learning because it mirrors how humans often learn. It's like studying for an exam with an answer key in hand. We provide the algorithm with input-output pairs, where each input has a corresponding correct label or value. For example, we might show it thousands of emails, each labeled as spam or not spam, or images of animals, each tagged with the correct species. The algorithm analyzes these examples, looking for patterns that distinguish one category from another. What features make an email spam? What visual patterns identify a dog versus a cat? Once trained, the model can apply these learned patterns to classify or predict outcomes for new, unseen data. Supervised learning comes in two main flavors. Classification is for predicting categories like spam detection, image recognition, or medical diagnosis. Regression is for predicting continuous values like house prices, stock prices, or temperature forecasts. This approach is incredibly powerful and forms the backbone of countless real-world applications, from your email spam filter to facial recognition systems to recommendation engines. Unsupervised learning is fascinating because it works without any labels or guidance. The algorithm must discover structure and patterns entirely on its own. Imagine you have a massive data set of customer transactions, but no predefined categories or segments. You don't know what patterns exist, or even if any meaningful patterns exist at all. This is where unsupervised learning shines. The algorithm analyzes the data, looking for natural groupings based on similarities. It might discover that your customers fall into distinct segments based on purchasing behavior, frequency, or preferences, segments you never knew existed. The most common unsupervised technique is clustering, where the algorithm groups similar data points together. K-means, hierarchical clustering, and dbScan are popular algorithms for this. Another powerful technique is dimensionality reduction, which compresses high-dimensional data while preserving important information. This is crucial for visualization and for speeding up other machine learning algorithms. Unsupervised learning is incredibly valuable for exploratory data analysis, anomaly detection in cybersecurity, customer segmentation in marketing, and discovering hidden patterns in scientific data. It's especially useful when labeling data would be too expensive, time-consuming, or simply impossible. Reinforcement learning is perhaps the most exciting and dynamic form of machine learning because it learns through interaction and experience. Instead of learning from a static dataset, an agent actively explores an environment, taking actions and observing the consequences. Think about how you learn to ride a bike. Nobody gave you a labeled dataset of correct and incorrect movements. You tried, you fell, you adjusted, and eventually you succeeded. That's reinforcement learning in action. The agent receives rewards for good actions and penalties for bad ones, and over time, it learns a policy that maximizes cumulative reward. The key components are the agent, which makes decisions, the environment it interacts with, the state representing the current situation, the actions it can take, and the rewards or penalties it receives. This creates a feedback loop where the agent continuously improves its strategy. Reinforcement learning has achieved remarkable breakthroughs. It's how AlphaGo defeated world champions at Go, how robots learn to walk and manipulate objects, and how recommendation systems optimize for long-term user engagement. It excels in sequential decision-making problems, where actions have delayed consequences, making it perfect for game playing, robotics, autonomous navigation, resource allocation, and financial trading strategies. Machine learning has moved far beyond research labs and is now deeply embedded in our daily lives, often in ways we don't even notice. In healthcare, machine learning algorithms analyze medical images like X-rays, MRIs, and CT scans to detect diseases such as cancer, often with accuracy matching or exceeding human radiologists. They help predict patient outcomes, personalize treatment plans, and accelerate drug discovery. In the financial sector, ML systems monitor millions of transactions in real time, flagging fraudulent activity before it causes damage. They assess credit risk, optimize investment portfolios, and power algorithmic trading. Your favorite streaming services use machine learning to recommend content based on your viewing history and the preferences of similar users. E-commerce platforms suggest products you might like, optimizing for both relevance and business metrics. Self-driving cars are perhaps the most ambitious application, combining computer vision to understand the road, reinforcement learning for navigation decisions, and sensor fusion to create a complete picture of the environment. Natural language processing powers virtual assistants, chatbots, and real-time translation services, breaking down language barriers. Computer vision enables facial recognition, object detection, and augmented reality experiences. These applications are just scratching the surface of what's possible as machine learning continues to advance and democratize. Let's bring everything together and recap what we've learned about machine learning. We explored 3 fundamental paradigms, each with its own strengths and ideal use cases. Supervised learning is your go-to approach when you have labeled data and want to make predictions. Whether it's classifying images, detecting spam, diagnosing diseases, or predicting prices, supervised learning excels at learning from examples with known answers. It's the most widely used form of machine learning in production systems today. Unsupervised learning comes into play when your data has no labels and you want to discover hidden patterns or structure. Use it for customer segmentation, anomaly detection, data compression, or exploratory analysis when you're not sure what you're looking for. It's perfect for gaining insights from unlabeled data. Reinforcement learning is the choice for sequential decision-making problems where an agent must learn through interaction. If you're building game AI, training robots, optimizing resource allocation, or solving problems where actions have delayed consequences, reinforcement learning is your answer. So, how do you choose? Ask yourself these questions. Do you have labeled data? If yes, start with supervised learning. If no, do you have a way to define rewards for good and bad actions? If yes, consider reinforcement learning. If no, unsupervised learning might be your best bet. Remember, machine learning is a tool, and like any tool, success comes from choosing the right one for the job. Your machine learning journey starts now. Keep learning, keep experimenting, and keep building.